Now that we've seen a few data sets and some of the summary statistics we can calculate and plots we can create in order to get an understanding of our data, we'll now summarize some of the features of data in general. An observational unit is the person or thing on which measurements are taken, for which a number of different terms are commonly used. Examples of observational units that we've encountered already include country or territory in our life expectancy data, skeleton in our anthropological data, and soccer player in the data of salaries of New York Red Bulls players. When we talk about a variable, we're talking about a characteristic that we've measured on an observational unit. In our life expectancy data, this includes, of course, life expectancy as well as region of the world. In our anthropological data, variables include age at death, sex, BMI, the estimated age at death, the difference between the actual and estimated age at death, which is an example of a variable calculated from other variables, and the salary of our soccer players. An observed value or observation is our data. It is the actual value of a variable for one of the observational units in a dataset. Data are arranged in rows and columns, with one row for each observational unit and a column for each variable. Many different file formats are possible for data, such as spreadsheets and comma-separated values. If you explore the data files used in this course, you'll find that we're supplying the data in plain text files, with spaces separating the observed values of the variables. Note, as here, that categorical variables can be coded multiple ways, including as numbers. Here, a sex of 1 indicates a male and 2 a female. It's not a quantitative variable, however. As we've already seen, variables can be of various types. A variable is quantitative if it takes on numerical values for which arithmetic operations make sense. For a quantitative variable, saying that one observation is twice as large as another has a practical meaning. If one soccer player's salary, say, is twice that of another, that has a clear meaning. Similarly, saying one soccer player's salary is $10,000 more than another player's has a clear, mathematically precise meaning regardless of how much each soccer player earns. This is characteristic of a quantitative variable. Some examples of quantitative variables we've seen include life expectancy, the actual age of a skeleton at time of death, the estimated age for that skeleton, the difference between those two ages, the estimated and the actual age, and salary of the soccer players. A categorical variable records into which of several categories an observation falls. As we saw in a previous video, we treat categorical variables with different summary statistics, such as relative frequency, than we use for quantitative variables. Some examples of categorical variables we've seen include sex, which is categories male or female, BMI, when we consider it as the standard classifications of underweight, normal, overweight, and obese, and region of the world, which had 6 categories in our data. And finally, there are ordinal variables, which have a natural order. Unlike quantitative variables, the differences between two values of an ordinal variable may not be meaningful. Sometimes ordinal variables are treated as quantitative, but when doing so, we need to be careful if a quantity like, say, the mean, truly makes sense. However, the median or middle value typically does make sense for an ordinal variable. An example of an ordinal variable we've seen is the BMI classifications, since underweight is less than normal, which is less than overweight, which is less than obese. Another example of an ordinal variable is the response to a Likert item on a questionnaire, where the respondent gets to choose from strongly disagree, disagree, and so on up to strongly agree. In earlier videos, we talked about outliers and their effect on calculations of summary statistics. In the New York Red Bulls salary data, there were 2 players whose salaries were much larger than every other player's salary on the team. This happened as a result of the designated player rule. This is a defining feature of an outlier, that it is separated from the rest of the data. Outliers shouldn't be ignored or routinely removed from the data. It can happen that an outlier is a mistake. In a data set of ages, say an age of 555 is clearly impossible and was likely a typo. Cleaning data by correcting errors like this is an important first step when dealing with a new data set. It's important to try to find out the reason for unusual observations. When outliers are not mistakes, they might be the most interesting feature, and removing them would remove an important aspect of the data. But, as we've seen in previous videos, they can sometimes have an overly influential effect on summary statistics that are not robust, and they must be treated with care in the analysis. It's not unusual to report findings both with and without outliers. Sometimes a data set can include missing values. Observed values can be missing for a number of reasons. In the anthropology data set of age estimates on skeletal remains, we've been looking at estimates of age at death that were taken using the DeGangi method, and the data we're using is a random subset of skeletons chosen from those for which the first rib, which we need for the DeGangi estimate, was intact. It's possible for any skeleton that the first rib might be missing or damaged so that a DeGangi age estimate cannot be made, and the age estimate for the skeleton would be missing. Sometimes the fact that a data value was missing tells us something about what it would have been had it been observed. Imagine a scale for measuring a person's weight that only goes up to, say, 100 kilograms. Any larger subjects who were part of the study using this scale would have had a missing value for their weight. Not including them in the analyses would bias the results by, for example, having a mean weight that was smaller than the actual mean weight would have been had the larger subjects been included. Or imagine a study where some subjects dropped out because they weren't doing well. Carrying out analyses without these subjects would make us think that the subjects as a group did better than they actually did. These types of situations require a lot of care. For our skeletal remains, we don't expect that a missing first rib has any relation to the age of the skeleton at time of death or to any other features of the skeleton such as sex or BMI or to the estimate we would have got. It may be reasonable then to assume that excluding skeletons for which we have a missing value for the DeGangi age estimate doesn't have any effect on our analyses, and we can continue to work with the dataset without them. But anytime we encounter a dataset with missing values, we must consider carefully why they were missing and whether the fact that they're missing might bias the results of our work.